This is chapter 22.5 on polymers. So the main learning objectives for this section is going to be about the properties of polymers, so like the structure, the shape, and kind of what the atoms and bonds dictate. The other thing we're going to do is discover the different types, so like which atoms are involved in creating the shape and the structure. And then lastly, we're going to explore polymers based on ethylene and which types we can achieve through that. So a polymer is just a large chain-like molecule that is built from small building blocks called monomers. And we see these all the time in our everyday lives through like plastics and like naturally in our body through like proteins. A thermoset polymer is a substance that cannot be softened again or dissolved after it's been molded. And then a thermoplastic polymer is a substance that can be remelted after it's been molded. So they're like opposites of each other, and this is where we get a name for the common things that we call plastics. So when individual polymer chains are drawn out into threads, the chains actually line up, and this makes the substance more crystalline. This leads to an increased hydrogen bonding between the adjacent chains, and this increase in crystallinity, along with the resulting increase in hydrogen bonding, actually leads to stronger fibers. So it would probably look something like this, where you have two chains right side by side each other, and you'd see an increase in hydrogen bonding between these. And as you can see, they are lined up right next to each other. And cross-linking is the existence of covalent bonding between adjacent chains, and this also accounts for the strength and toughness of these polymers because it pulls the adjacent chains closer together. So now we'll talk about polyethylene in specific, but the main attribute of polyethylene is its high molecular mass, and because of this high molecular mass, it results in a high strength in the interactions between specific points, which is actually kind of quite small in just a tiny perspective, but if you draw out into a long chain, they actually add up to a very large value. And there's also a lot of physical tangling between the chains, which also makes the reaction stronger and the polymer stronger. However, a material like polyethylene can be melted, like that we talked about before with the thermoplastic, into a new shape. And this melted state can like readily flow between molecules, which makes it a lot easier to move around. So we can actually apply this thinking when we compare intermolecular forces in polyethylene and polyvinyl chloride. So the unique thing about polyvinyl chloride is that it actually has polarity in the carbon-chlorine bonds compared to the carbon-hydrogen bonds. And this increase in polarity creates a larger dipole, creating dipole-dipole interactions compared to the London dispersion forces of the polyethylene. And these dipole-dipole forces are a lot stronger. So as a result, the intermolecular forces in polyvinyl chloride are a lot stronger. But another thing you should also take into account is that chloride is a lot heavier than hydrogen. So even if we were just to compare on the side of London dispersion forces, polyvinyl chloride would actually have much more because of their higher molecular mass, which results in a lot more instantaneous dipoles. So addition polymerization is actually one of the most basic formations of polymers. It's just a process where the monomers just add together to produce the polymer. And the way it works is that it's started by a free radical, which is a species with an unpaired electron, and it attacks and breaks the bond of an ethylene molecule to form a new free radical in the case of polyethylene. And then that new free radical attacks another ethylene, and the process continues and makes longer and longer chains. And a bit of a diagram is seen below. So the free radical, the OH, with that electron attacks the double bond between the carbons, and it creates the basis for the polyethylene. And then the new free radical created attacks another ethylene molecule, and then you get a huge chain. And eventually you'll have a giant polymer. The next type of polymerization is condensation polymerization. And basically what this just means is every time we make the polymer chain longer, so every time we extend it, a small molecule is also produced. So in the case of this example, when this nylon is formed, a water molecule is also produced as a byproduct. So comparing these two different types of polymers, a copolymer is just a polymer formed when two different types of monomers combine. So here we have hexamethyl adenamine, I'm sorry if I pronounced that wrong, and adipic acid, and they combine to create the nylon that we discussed before. There are two different types of monomers, and then the polymer they form is unique. And then a homopolymer is a lot more basic. It's just a polymer chain formed when a single type of monomer are added together. So we see this in the example of polyvinyl chloride, and it's just vinyl chloride units being added together, and then eventually you get a polyvinyl chloride chain. So a polyester is a specific type of polymer that is characterized by its functional groups, and it involves a carboxylic acid and alcohol, and they form an ester group. And an example of a polyester is Dacron, but you see the general formula of the polyester is going to be a carbon attached to a double bonded to an oxygen, but it's also attached to another oxygen that is in between a hydrocarbon group, which is what the R symbolizes, and then the carbon is also attached to another hydrocarbon group. The explanation by word might not be as helpful, but when you look at the picture as you see it there, just remember that R can be any type of hydrocarbon group. So polyamide is actually just a copolymer formed when an amine functional group reacts with the carboxylic acid functional group. And the general formula is shown right there, although you see that the N represents that it can be a number of groups that can allow it to form a long chain. And a very famous example of a polyamide is Kevlar. So because of these long chains and the interactions between the hydrogen and the oxygen, as you see there, it's actually really strong, and it's used in a lot of industrial use and military use. So if we're characterizing specific types of chains, isotactic just means that the substituent group you're looking at, so in the case of the examples below, it's CH3, they're all on the same side of the chain. Syndiotactic means that they kind of alternate from one side to the other. And atactic just means they're randomly distributed. They can be on either side of the chain and on either side of the carbon. So these are the three different types, and we're going to apply them in the examples on the next slide. So if we ask the question, which makes a stronger fiber, the isotactic propylene or an atactic propylene? Well, the isotactic propylene, along with actually a syndiotactic one as well, they have a regular arrangement of their atoms, so it has to be very specific. It has to be in a certain pattern. And because of this, it's actually really easy for them to pack together into crystals and fibers because their pattern allows them to match together really nicely. And if there's no order in like the atactic ones, you can't really pack them that well. So the forces keeping them together are going to be weaker. And because the molecules in the isotactic and the syndiotactic are the same shape, this results in stronger fibers than the atactic ones.